And we'll continue with the problem that we were solving. And it turns out that I was right. The answer for that problem, let me bring it up. I don't know why I got confused. I should have just rolled with it. So jolt your memories. This is what we were talking about. The next one. Right? This one. So the recap, we had a diode D1 and a Zener diode D2, two resistors R1 and R2. In the previous example, we saw how it could form a voltage divider network and V out over V in, the transfer characteristics would have a slope of minus half, minus 0.5. So in the Zener diode, we go through and do the same analysis on Thevenin equivalent circuit, in reverse bias, and then in forward bias. So in the negative half cycle, the Zener diode turns on. It requires 5 volts to turn on. And once it turns on, we can write VZ is equal to 5 volts. So I think the difference in my notes and the one I did here was I chose the diode notation instead of the Zener notation. The Zener notation means the cathode of a Zener diode will always have plus VZ. So instead of plus minus, it should be minus and plus. Regardless of the notation, the equations and the final solution would turn out to be the same. So I'll show you both. Okay. So if we have this, the equivalent circuit is here. VO. And V out includes VO, right? So if I was to apply KVL, I can apply it in this direction. So this would be opposite. Minus and plus. Okay. For all V in input voltages, 5 volts or greater, right? If it's less than 5 volts, it's off. Right? If it's less than 5 volts, it's off. If it's greater than 5 volts, it's conducting, but it holds a 5 volt voltage drop across it. So it behaves like a constant voltage source of 5 volts. Hence that representation. So now if you apply KVL, what is the total value of the voltage that is being applied to the two resistors? V in plus 5. Right? V in plus 5. So the voltage V out would be this equation. Right? V in plus 5. So it'll be total voltage being applied and the voltage divider. So the drop that is across R2. The drop that is across R2. Okay. So now let's say, let's actually use the numbers. Let's say V in is 6 volts. So what is the total voltage being applied to the two resistors? 11. So the V in plus 5, 11 volts being applied to the two resistors. So what is the voltage drop across R2? Just across R2. 5.5. 5.5. So VR2 is 5.5. Is right here. 6 plus 5. Let me rewrite again. And this is the voltage drop applied to R1 and R2. Okay. Total being applied. Let's write it down here. Total voltage applied to R1 and R2. Where did it go? (11 times R2 over R1 plus R2). Hence, 5.5. V up is so what is now? Yes. So I'm looking at the total voltage that is being applied to R1 and R2. Okay. Okay. So this was what I was trying to do last time. Okay. If I take the diode voltage, meaning it turns on, then the polarity reverses. Polarity reverses. If the polarity reverses, then if I apply KVL, it becomes 6 minus 5 being applied to R1 and R2. The values of the magnitudes do not change. It remains the same. Just becomes 6 minus 5. Does everyone see what I'm saying? No. Okay. So I took, so here in this diagram, I'm taking VZ with my anode as negative and cathode as positive because it's Zener diode. Okay. So I would add V in. I would add VZ to V in because they would appear in series to R1 and R2. Okay, they would appear in series to R1 and R2. So if I reverse this polarity, which is minus and plus for V in, right? This is the negative half cycle. So it's, but if I apply the opposite polarity, then my VZ, or actually the diode voltage, will be subtracted. And so now if I apply this to R1 and R2, the voltage across these two resistors would be V in minus VZ. The actual magnitude of the voltage does not change, but it remains exactly the same. So in this case, V out is taken across R2 and it is taken across Zener diode voltage of 5 volts. And they have the opposite polarity. That's where I got stuck. Okay, that's where I got stuck. But now look at this. What is the result of this for 6 volts? 1, right? 1 volt. So now what is the voltage across R2? 0.5, right? Now, what is V out? 5.5. Same answer. So it doesn't matter how you take it. Either you take it VZ plus at the cathode or plus at the anode, you would still have the same answer. Do you have a question? Oh, okay, just. Oh, before I forget, Friday quiz today is gonna start. Well, actually, no, it started at 12 noon, and it's all the way till midnight tomorrow, not just for today. So students have the option of beginning anytime today, all the way up till midnight tomorrow. It's gonna run for, let's say it's the same standard time of 30 minutes. So the latest you can start would be 11:30 tomorrow, but don't wait until then. So if you wait until then and the system goes down for maintenance, you won't be able to do anything. Yes. We did that here also. V in minus 5.
Okay, that's in the negative half cycle.
Negative half cycle. It only functions in the negative half cycle, right? Because in the positive, it's going to act like a forward bias diode, so it's just going to be a short circuit. No voltage drop required because you're not considering, you're just using ideal diode analysis. Okay, so forward bias is all a short. Even in reverse bias, it's not going to turn on until it passes 5 volts threshold voltage. Okay, so even until then, V out will be equal to V in. It's only afterwards that it drops. Okay, it's only afterwards that it drops. Right. So there were a couple more. Let's see. And these problems were actually interesting. So there were a couple of questions students asked, like, how are gates formed? A typical answer always is transistors and MOSFETs, any kind of BJT or a FET or MOSFET. So let's take a look at these circuits, and then you tell me how these circuits behave. All right, so first up is a 2-diode circuit. Actually, both of them are 2-diode circuits. So you have diode D1 and you have diode D2. And both of them are connected to a resistor. You're taking output V out right here. And then you're applying input VA and VB. And you're asked to determine the output voltage VO. Again, using the same ideal diode analysis. So the conditions are VA and VB. All right. 0 volts or 5 volts. VB could be 0 volts or 5 volts. Analyze the circuit and determine VO, the output voltage for all combinations of the inputs. all combinations, and use ideal diode analysis. Okay. So first case, let's take VA and VB are both 0 and 0. 0 volts and 0 volts. Okay. So then, are the diodes on or off? Diodes are off. If the diodes are off, what is VO? If anodes are connected to 0 volts, diodes are off, reverse bias. Diodes are not forward bias, basically. So diodes are off. If diodes are off, V out is connected across the resistor. There's no voltage, 0 volts. How about if VA and VB are 0 volts and plus 5 volts? What is D1? On or off? D1 is off. How about D2? On. So what is V out? So how much is it? Are you showing me the finger? Or fingers? Showing me 5 fingers in my classroom. It's 5 volts, yes. What about 5 volts and 0 volts? D1 is, D2 is. So my V out is 5 volts. How about when VA and VB are both 5 volts? Both diodes are on. So my V out is 5 volts. Now create a table for the inputs and the outputs. What do you see? What was the conclusion? It's an OR gate. Absolutely. So again, if we create a table, we have VA, VB, and VO. We have 0 volts, 0 volts, 0 volts, 5 volts, 5 volts, and 0 volts, and 5 volts, and 5 volts. Output is 0 volts, 5 volts, 5 volts, 5 volts. Digital logic, 0. Logic low would be 0 volts, or at least 0.1, 0.2 volts, depending on the design of the system. Logic high, or 1, would be plus 5 volts or plus 3.3 volts. Modern digital logic circuits, but 5 volts. So a digital logic truth table, which is zeros and ones binary in circuit analysis, would be 0 volts and 5 volts. So you can implement an OR gate using simply 2 diodes. Does that make sense now? kind of, right? That's how it works. Underneath, everything is a circuit. Everything is an electric or an electronic circuit. Okay? It's logic gates, if we are working with like digital logic gates and we say binary system and everything. But again, machine, artificial intelligence doesn't mean it, it recognizes anything. It's still underneath. It's all still just circuits. We can say zeros and ones to work out the math and to implement the system, but then the circuit design is part of, it's a specialization within EE, how they design these circuits. Okay. Then let's look at another one. Let's reverse these diodes. If we reverse these diodes, what do we get? Okay. So instead of doing this and connecting the resistor to ground, let's change and flip the directions of these diodes. Connect the resistor to plus 5 volts and take V out from there. And then everything else remains the same. This is D1, this is D2. Parameters of the problem statement, everything remains the same. Ideal diodes. Determine V out for all combinations of VA and VB. VA and VB can take on 0 volts or 5 volts. All right, so now you write it down and let's work through this. You tell me what the answer would be. So we'll wait until everybody finishes.